Hello everyone, welcome to this video. In this video, we'll be studying about the properties of elements under homomorphism, right? So we already know if we define some mapping from G to G bar, then that mapping is homomorphism whenever we have the operation preserving property with us, correct? So now we assume that from this group G, we take some small element small element G from this group capital G, right? The first property here tells us that this phi, which is a mapping, this carries the identity of the group G to the identity of the group G bar, right? So if you take some identity here, it will map to some identity here, right? So this is what it tell you. And remember that the same property we have studied for isomorphism as well, right? So, and the proof is also similar. Let me give you the proof again. So here, if we have E1 representing the identity of the group G and E2 representing the identity of the group G bar, then we have to prove that phi of E1 is equal to E2. So what we do, we assume that this is equal to G. So G is your phi of E1. So what would be G square? It would be phi of E1 whole square. So whole square means you can write it twice, correct? And now because we have the operation preserving property, so you can combine the elements, because phi of A, phi of B by the operation preserving property is equals to phi of AB. So you can write it like this, phi of E1 E2. So you can write E1 E2 as even square, right? So E1 square is E, that you know, and what is phi of E1? That is G. So from here you obtain G square is equals to G, right? So what you can do from here, you see, if you post multiply both sides with G inverse, so you have G is equals to E2. Why E2? Why? Because G is G is what? Phi of E1, and it is a member of G bar. So here G inverse would be the identity of the group G bar. Hence we have E2 over here, correct? So that means you have phi of E1 is equals to E2, and this is what you wanted to prove in the first property, correct? Now let's move on to our second property. The second property here says that phi of G raised to power n is equals to phi of G whole raised to power n for all n in the set of integers, correct? So this is the property. So let's this is also very simple property. Here for this property we take the left hand side, phi of G raised to power n. So G is appearing n times, so you can write it like this, G into G into G into G. How many times? Total n times, correct? Now because this is a homomorphism, phi is a homomorphism and it has operation preserving property, so you could separate it out for each individual element. So you can write it like this, phi of G, phi of G, phi of G into phi of G. How many times? In total n times, correct? Why? Because phi is operation preserving, and because this phi of G is now appearing how many times? N times. So you can write it like this, phi of G whole raised to power n, and this is what we wanted to prove here in this second property. So you see the proof of these properties are quite simple. We will be looking at more properties in the next video. Well, that is it for this video. Thank you for watching.